Hello everyone, my name is Zhao Zhu, and I'm a second-year graduate student at Shanghai Tech University. Let me present our work, selectively combining multiple college goals in search-based unit test generation. This work is jointly done by Professor Yu Mingzhou, Professor Chun Fang, Professor Zheng Yucheng from Nanjing University, and my supervisor, Professor Yu Xiantang, and myself. Search-based software testing is a popular technique for generating unit tests. It casts unit test generation as an optimization problem. Specifically, it regards each goal of branch coverage as an optimization goal and tests as solutions. Then, it uses genetic algorithms to evolve tests until all goals are covered or timeout. Here is an example. We have a simple program containing a predicate A is equal to 10 in line 2. This predicate yields two branches, the true and the false. We focus on the true branch. In this example, we can formulate a simplified fitness function for it. The absolute value of A minus 10. The fitness function can measure how far a test covers the branch. A test covers it if the function returns 0. Firstly, search-based software testing initializes some tests randomly. Then we can calculate their fitnesses. Note that the number 1 test gets the worst fitness, so we only select the other 2 tests for further evaluation. We do a mutation on these 2 tests. A mutation means doing a slight change on an existing test. For example, we mutate 8 to 9 to get the number 4 test. After mutation, we calculate their fitnesses and make a selection again. Since number 2 and number 4 get the top 2 fitness, we keep them, then we do a mutation again. After calculation, we find that the best tests come out. Overall, this is a typical process of search-based software testing. However, branch coverage is not enough. In 2015, Rojas and his co-operators pointed out that the test suites optimized for branch coverage can achieve higher code coverage than many written ones. However, they may not satisfy the expectations. We use this program as an example. We have 2 tests. Test 1 covers the true branch and test 2 covers the false branch. Hence, this test rate reaches 100% branch coverage, but developers may still not be satisfied. This is because last rate may throw an exception, since B could be 0, but these 2 tests do not capture this property, so developers do have some requirements going beyond branch coverage. To create a test rate satisfying the expectations, they introduce more coverage criteria. For example, exception coverage focuses on the number of exceptions a test rate triggers. Output coverage focuses on the diversity of the method's return values. Currently, the state-of-the-art search-based software testing tool USuite uses the fitness function combination of these 7 criteria and the branch coverage as a default configuration to guide genetic algorithms. A side effect of introducing more coverage criteria is that coverage decrease happens. Here is a partial result of our experiment. After applying one of the state-of-the-art genetic algorithms, host regeneration to 85 Java classes with at least 200 branches, we found that coverage decrease happens in every criteria. For example, when we only use branch coverage to get the genetic algorithm, the average coverage is 51%. When we use these 8 criteria, the average branch coverage is 41%. The coverage decreases by 10%. In our opinion, the decrease is related to these criteria fitness functions. Let's take a set. These graphs show rough versions of them. For example, the first one is branch coverage. When a test does not invoke the method containing the target branch, the fitness is always 1. When the test invokes this method, it returns a normalized branch distance reach 0 to 1, showing how far to cover the branch. This function is a good one to get the genetic algorithms since it is continuous, monotonic in neighborhoods, and has a non-zero gradient in the most range. The second one is exception coverage. Its fitness function is a plateau and has a discontinuous point since search-based software testing would not know which line has an exception until a test triggers one. This function downgrades genetic algorithms to random search since it cannot provide any gradients. Hence, We know that different criteria fitness functions vary in ability to get genetic algorithms due to their internal properties. As a result, the combination creates a complex search space, potentially containing many local minima. This complex search space undermines the efficiency of genetic algorithms. To cope with this coverage decrease problem, we propose smart selection. It selects a subset of fitness functions. It should fulfill these two targets. Firstly, the selected subset improves the effectiveness of getting genetic algorithms. Secondly, this subset should avoid missing any properties captured by these criteria. For example, we have known that branch coverage is better than exception coverage in getting genetic algorithms. But the developers do want to get a test suite triggering as many exceptions as possible. So we definitely cannot just remove exception coverage fitness function only because we want to improve the efficiency of genetic algorithms. Here is an overview of smart selection. Its input is the 8 criteria, and its output is a subset of their fitness functions. Its first step is to group criteria by coverage correlation. Just as said before, we want to select a subset that is more effective in getting genetic algorithms, but we cannot actually remove a worse fitness function, since it reflects a requirement of developers. Hence, we need to know which fitness functions we can remove. So firstly, we group criteria by coverage correlation. Coverage correlation means that if a test suite gets a high coverage for a criterion, it may also get a high coverage for another criterion. In other words, these two criteria reflect many redundant requirements, so we could choose one of them as the guide. Secondly, in each group, smart selection selects a criteria to represent others. This representative has better fitness function and can reflect most of the properties in this group. After the second step, we choose the representative criteria. However, the other criteria may still have some properties going beyond the representatives. So for each of them, we select a subset from its coverage goals to keep its property consistent. Let's go into the first step. Specifically, we have definition for coverage correlation. Two criteria have a coverage correlation if the coverage values measured by them have a positive correlation for an arbitrary test suite. We use three rulers to determine two criteria that have a coverage correlation. One, there is some previous work studying the coverage correlation for some criteria. We adopt their conclusions. Two, criterion A is criterion B with more requirements. Three, for an arbitrary test suite, we can prove that coverage A is nearly equal to coverage B. We leverage ruler 2 as an example to show how it works. Ruler 2 is that if a criterion A is criterion B with more requirements, we say that they have coverage correlation. For instance, DBC, direct branch coverage, is BC branch coverage with an actual requirement. A test case must directly invoke a method to cover its branches. Here is an example. In line 2, the master program 0 has a predicate. We focus on its true branch. There are two tests on the right side. The first side test calls this branch by calling program 1, since program 1 calls program 0. Hence, it fulfills branch coverage, but it fails at fulfilling direct branch coverage. The second test fulfills both of them, since it calls this branch by directly calling program 0. Hence, we can conclude that for any test suite, we have coverage BC no less than coverage DBC, so they have a coverage correlation. In conclusion, we cluster 8 criteria into 4 groups using 3 rulers. In the second step, in each group, we sort criteria by their effectiveness in getting genetic algorithms, then select a representative criterion. We leverage the group branch coverage, direct branch coverage, lag coverage, and weak mutation as an example to show the process. Compiling their fitness function, we can sort them into 2 subgroups. Lag coverage and weak mutation are worse than branch coverage and direct branch coverage. However, we cannot quantitatively sort the Let 2, since there are two similar criteria, so our sorting is a rough version. After sorting, we keep branch count and direct branch count, but we want to keep only one representative criterion to get a smaller subset of the fitness functions. So we use another perspective to determine which one we chose. Recall that direct branch coverage is branch coverage with an actual requirement, so we can conclude that if a test covers a goal of direct branch coverage, for example, a child branch in a line 2, it definitely covers the corresponding goal of branch coverage, but the opposite does not hold. As a result, direct branch coverage can fully represent branch coverage, so we chose it as the representative criterion. In conclusion, we select 4 representative criteria from 4 groups. There are no exception: top-level master coverage, direct branch coverage, output coverage, and exception coverage. The other 4 criteria are unselected. The first and second steps have selected a subset of fitness functions. However, this subset cannot include the 4 properties of all criteria. Here is an example. On the left side is a simple program. In this program, the child branch of line 2 contains 2 lines, 3 and 4. On the right side is a test suite. Assume that it is generated using the representative criteria as the guide. The test suite calls all branches of the predicate and checks an exception in line 3, so it covers 100% of branches and exceptions. But this test suite does not cover all lines since it misses line 4. The reason is that the test suite covers the child branch but throws an exception in line 3. The genetic algorithms could ignore line 4 since we only use the representative criteria that do not include line coverage. So here is the challenge. There are some properties of an selected criteria going beyond the representative ones. To overcome this challenge, we select a subset from each unselected criterion's fitness functions. This subset includes all properties of this criterion. To make it, we introduce a new concept, subsumption relationship. Here is its definition. Two coverage goals having a subsumption relationship denotes that if a test covers one goal, it must cover another goal. We leverage line coverage to explain this concept. Here is a program. We can say that line 3, 4, and 5 form a basic block. In such a basic block, the last line subsumes the others. That is, line 5 subsumes line 3 and 4, which means that if a test covers line 5, it definitely covers line 3 and 4. Hence, if a test suite covers all basic blocks last lines, it covers all lines. As a result, the set of last lines forms our desired subset. In conclusion, we select a subset of goals for each unselected criterion. Finally, we join the fitness functions of them and the representative criteria to get genetic algorithms. The last part is summary of experimental results. The comparison of smart selection and the original combination. The original combination is to combine all goals. We evaluate them with 3 state-of-the-art genetic algorithms: host regeneration, Moza, and Dynamoza. We leverage the host regeneration to expand these tables. For all the 400 Java classes, smart selection brings nearly 2% average coverage improvement. 141 classes show a statistical difference between smart selection and the original combination. That is, 259 classes show indifference to these two approaches. In 141 classes, the proportion of smart selection outperforming the original combination is nearly 85%. Specifically, for 85B classes with at least 200 branches, smart selection brings nearly 4% coverage improvement. 51 classes show a difference between smart selection and the original combination. In 51 classes, the proportion of smart selection outperforming the original combination is 98%. From the data, we can find that the advantage of smart selection is more significant in the bigger classes, since the bigger classes have more coverage goals bring in most fitness functions. Furthermore, the advantage of smart selection decreases from whole tree generation to Mozart and to Delmoza. You can find a related discussion in our paper if you are interested in it. In summary, firstly, multiple criteria fitness functions bring a more complex search space, undermining the performance of genetic algorithms. Second, smart selection provides a solution to reduce the number of fitness functions. Thank you for your listening. Any questions or comments?